Okay, so this will be our last video for the Test 4 review. And these are our application problems. So on number 13, it says the sum of $25,000 is invested at an annual interest rate of 3.25%. Find the account balance after 8 years if the interest is compounded monthly. Now, because our interest is compounded monthly, we're going to be using this first equation here, and n is equal to 12 because of the fact that it's basically we're applying interest to the account 12 times a year, every month. The 25,000 is our starting amount, which we call P. And of course our interest rate, in this case we move the decimal 2 places to the left and we write it as a decimal. It's 0.325. And of course 8 is our time because it's 8 years. Alright, so let me go ahead and write down the formula. And let's plug in our numbers. So P is 25,000 times 1 plus R, which is 0.0325, over N, which is 12. And then it'll be NT power, that's 12 times 8. So you want to make sure when you put this into the calculator you're getting the right answer. So step 1 is getting all the numbers into the right place in the formula. And then once you've done that, you just got to make sure you plug this into the calculator correctly. And you get $32,411.86. So our money grew by a little bit in 8 years. Let's look at number 14. It says if $8,500 is invested in a long-term trust fund at 5.4% and the interest is compounded continuously, so this time is different, find the amount in the account after 25 years. So for continuous interest, we use what I call the Pert formula. That's this one here. But you could also use this one. It's actually very similar. Instead of calling it an interest rate R, it's K, which has a growth rate. It works pretty much the same way. So you really could use either formula. So let's go ahead and write our formula down. So I'm going to use the Pert formula. We know our P is 8,500. Our interest rate's going to be 0.54. Oops, that's not right. How about 0.054? And we said it was compounded continuously, and notice T is 25 here. And so let's plug in our numbers. We get 8,500 times E. Let's see, R at 0.054 times T, which is 25. And so when we plug that into the calculator, again, we get 32,000 something. It's $32,788.12. All right, for part B, it says, how long does it take your investment to double in value? So sometimes students get stuck with this here, but notice we're starting with 8,500. That's our initial investment, and we want it to double. So we go from 8,500 to 1,700. So let's go ahead and write down our formula. And our A, the amount we want this to grow to, is 17,000. The original amount is 8,500. Notice it says how long does it take? So basically we're looking for T here. And so we have all the other values. And so this is the equation we need to solve. Now, this is an exponential equation with an extra number, that 8,500. Notice we have base, exponent, answer. And so we're going to want to switch forms. But before we can do that, we need to get rid of that 8,500 by dividing. So we'll divide each side by 8,500. And you'll get 2 is equal to e to the 0.054t. Now consider that 1,700 or 1,000 is double what we had here because we were asked to find how long it takes the investment to double. It turns out that you're always going to get 2 on this next step when you're doing a problem like this because of the fact that the one number is double the other number. So let's go ahead and switch forms now. This becomes a log base e of 2 is equal to 0.054t. Again, if you want to check it, e to this power equals 2, which is what we've got. Let's go ahead and write that in the natural log form. That's how we normally write it. And we need to divide both sides by 0.054. Natural log of 2 divided by 0.054 is about 15.4. So it takes about 15.4 years. All right, let's move on to the next slide. So according to some estimates, the population of Texas has grown from about 25.1 million in 2010. That's when they took the last census, to 29 million in 2020, and we should get a more accurate number perhaps after they finish the census, since they're currently working on it. But anyway, it says find the rate of growth, then write the exponential growth function for the data. So first of all, we're going to be using the growth function p of t is equal to p naught times e to the kt power. Now it's important to remember what each part represents. P of t is the population after t years, or the amount after t years, depending on what you're dealing with. Here we're dealing with population. P naught is the starting population, or the starting amount if we're not talking about people. And then k is our growth rate, and t is our time, and it's in years. So in this problem, 25.1 is our p naught, and 29 would be our p of t. And notice it went from 2010 to 2020, that's 10 years, and so our t is 10. All right, so let's plug in our numbers. P of t is 29. P naught is 25.1. Again, these numbers stand for million people. And then this times E. We don't know what K is. That's going to be our growth rate. That's what we're looking for. But we do know T is 10. And so, again, we've got this extra number here. We want to put this in exponential form, where we have base, exponent, answer. And so we need to divide both sides by 25.1. Now when I do that, I have a choice. I could leave it like that when I do my calculations as the fraction 29 over 25.1. I like to just go ahead and write it as a decimal answer, but I include a lot of decimal places. So you get 1.15538 is equal to e to the 10k power. All I did was change the 10 and k as far as the order. We can do that with multiplication. So this is an exponential function. Let's change it to logarithmic form. It'll be the log base e of 1.15538 is equal to 10k, which we would write as ln of 1.15538 equals 10k. We'll divide each side by 10. And so we end up with k equals 0.0144. Now remember, this is the growth rate, so we normally write that as a percent. That's 1.44%. And we're also supposed to write the exponential growth function. And so that's the original function, p of t equals 25.1, our starting population, times e to the 0.0144t. In part B, it says estimate the population in 2025 to 2 decimal places. So basically, 2025, now our initial population was 25.1 in 2010. So we're going to want to subtract 2025 minus 2010. That's 15 years. And so we're just finding p of 15. So plug 15 into our function, and when you do that, you should get 31.15. And actually, I should have written it that way. I just realized I said to 2 decimal places. So about 31.2 million, or really it should be 31.15 if we're going to use 2 decimal places. Okay, we got one more problem. It says if the model is correct, how long would it take for the population to reach 40 million, which is about the current population of California? Well, we still have our same model, P of t equals 25.1 times e to the 0.0144t, or this is our growth function for this situation. Now basically P of t here is 40 million. That's our growth, or that's what we want it to be after so many years. We don't know how many it's going to take, or I should say that's what we want to know, is how long would it take. So P of t is 40, and so we'll plug that into our growth function, and then we'll do a lot like we did on the previous slide, and really like the last problem, or problem A. Let's go ahead and divide both sides by 25.1. We're going to get 1.5936 is equal to e to the 0.0144t power. And when we change to log form, it'll be the natural log of 1.5936 is equal to 0.0144t. We'll divide each side by 0.0144, and you get t is about 32.36. Remember, that's a time in years. And so our final answer is about 32.4 years. And so it's going to take some time. All right, we'll go ahead and stop right there.